Hey, welcome back. All right, we're back to some related rates on the Related Rates channel here. So we did some Pythagorean theorem problems, and now we're going to look onto a different type of problem. And I'm not going to give it away yet and tell you what kind of problem it is. I'll let you kind of look at it and figure it out yourself. But here is the situation. We have a stealth fighter jet, and it is flying overhead, and this spotlight here, the searchlight, is under its path. It tracks it, and we're trying to find out how fast this is pivoting when the plane is 1,000 feet east, when it's directly overhead, or when it's 5,000 feet west. So let me show you a little bit of the animation here. Let me show you the storm before that rainbow comes about. So there it is. So the problem that we're going to do is one where it's 5,000 foot west. So here it is. Now if you noticed what's different about this problem, we still have right triangles that we're dealing with, but unlike the Pythagorean theorem problem, we do have two sides, but we're not trying to find this hypotenuse. We're not trying to find this third side. We're trying to deal with an angle. So you can probably already think about what we're going to be doing with this, dealing with angles and sides of right triangles. And if you were thinking, say it out loud, no one's listening, trigonometry, you would be correct. We are going to do some trig. So let's get to solving this problem right away and doing some related rates. So let's first we draw our triangle. Remember our dreads. So here's our triangle. Oh, it's a beautiful triangle, isn't it? We don't need to see that. So we have our right triangle. Remember, the altitude was 4,000 feet. And we have our airplane right here. We have our searchlight down here. This was theta that we were trying to track how fast it was going. So if we go back just for a moment and look at it, we have x sub t. They're calling it a function. I'm just going to call it x. It means the same thing. Now what we need to do is come up with some rates. We saw that, let me go back again, I'm sorry. We saw that this is changing at 700 feet per second, so we know that. Alright, so we need that rate, which is dx dt. So we know dx dt is 700 feet per second. And we're looking for how this is pivoting, the change of this. So we're looking for d theta dt, which is a new rate for us. And we're looking at it when this guy up here, this distance is 5,000 feet to the west. Now, does it matter? And this is a question to think about as we go on. Is d theta dt going to be affected whether it's 5,000 feet to the west, or whether it's 1,000 feet to the east, or whether it's directly overhead? So think about that. Is that going to affect this angle, this rate of how this angle is changing? Okay, so we have to look at a relationship here for dreads. We have our rates. We have an equation that's going to relate theta, x, and 4,000 together. Can you think of something? We have a right triangle. We already kind of mentioned trigonometry. What trigonometric relation will have this guy, this side here, and this one right here? If you guessed opposite over adjacent, or if you guessed tangent, you would be correct. The tangent of theta is equal to the opposite over the adjacent. Cool. So we have our equation. Now the reason why 4,000 is in there and not 5,000 is 4,000 is what we call a constant. That altitude is not changing in our problem situation. The 5,000 is changing. It is, as this plane moves away, 5,000 gets larger, or depending on where we were coming from, if you look back, 4,000 never changed. However, x, or x of t, constantly changed. So keep that in mind as we do this. So now that we do this with dreads, we have the diagram, we have the rates, we have the equation. Derivative, let's take the derivative. I will do the hard part for you. Okay, that is x over 4,000. So that just becomes 1 over 4,000. But we can't forget, we're going to do implicit differentiation here because we're taking all the derivatives with respect to t. So we have to multiply by dx dt. And over here, who remembers the derivative of tangent theta? If you said secant squared theta, you would be correct. But again, we're differentiating with respect to t, so times d theta dt. Here's our derivatives. So d(r)(e)ds, substitute and solve. Okay, well, we're looking for d theta dt, so I'm going to solve this. I'm going to leave this right here, and I'm going to divide both sides by secant squared theta, just to get everything on the other side. Now you can try to make this pretty if you want, or you can just leave it as it is. So here's my d theta dt. It's 1 over 4,000 times dx dt all over, and I'm running out of space, secant squared theta. Now substitute and solve. Okay, let's see how hard that is. Substitute and solve. Okay, I have 1 over 4,000. I have dx dt, and the great thing is I'm given dx dt. Secant squared theta. I'm not given theta, so that means I'm going to have to find theta. Well, how am I going to find theta? Do I have enough information to find theta? I do. I have this side, and I have this side. We know this is all occurring when x is 5,000. So I can do tangent of theta equals 5,000 over 4,000. And now I'm looking for this angle theta, so I'd have to do the inverse. You remember the inverse tangent of 5,000 over 4,000. And you guys can do that in your head, right? No, I'm kidding. I don't expect you to do it in your head. So you would use a calculator, and it's really just 5/4 if all those zeros go goodbye-bye. And when I do this, I should figure out, remember it's in mode is radians. So we're going to have mode, and we're going to have 0.896 radians is our theta. So now I'm going to take this, I'm going to take this, and I'm going to plug it into this equation. I'm going to go to a new screen so we have some space. So d theta dt is equal to 1 over 4,000 dx dt all over secant squared theta. Now we said that dx dt was 700 feet per second, so I will multiply that by 700. And then we have to find secant squared of 0. I don't remember what it was. 896. Again, using your calculator, you can multiply this. Oh, this is easy enough. 700. Oh, I don't like that equal sign up there. I'm sorry. Sorry I'm talking a little fast. You can always slow this down, stop it, all that good stuff. But YouTube gives me some time restrictions on here. So that's why I'm talking a little fast. How do I calculate this in my calculator? There's no secant squared button on my calculator last I checked. So you might remember the reciprocal of secant is cosine. Yes, so you have to do 1 over cosine of 96, and we have to square that whole thing. And if you do that math in your calculator, you should get that d theta dt is equal to radians per second. So 0.068 radians per second is what you should get. Now, it's not asking how fast, or is it asking how fast? Whoops. Sorry. Let's see. So it's still flying. It says how fast. So the good news is how fast. We don't care about sign, meaning positive or negative, because it's a speed that we're dealing with. But sometimes, if it was just asking for d theta dt, since it was on the left side, this may appear to be negative, or you might find an answer to be negative. But again, it's asking how fast, so that is our answer. Cool. So now what I would like you to do is I'd like you to take a moment, and you can try, and we'll go over in class the answers if you want to do that. I want you to try the exact same situation, but I want you to get it when x is 1,000 foot to the east and then directly overhead. So what does that look like? Well, 1,000 feet to the east, would be the triangle would look over here. The altitude hasn't changed. The theta hasn't changed, but now this is 1,000 feet in this direction. And then directly overhead, 4,000. Directly overhead is right there. How does that change? What is theta? Think about that. Some ones to think about. So again, look at this video as many times as you want. We're going to be doing some more trigonometry, if you will, in class. But hopefully you found some success with this video. Johnstone, out.